Hello everyone, and welcome to my new computing series. Throughout this series, I'm going to be explaining different aspects of the computing subject. If, for example, you picked computing for your GCSEs, then these videos might come in handy, as I will be explaining topics from hardware to software in understandable terminology with diagrams to help. And even if you're not a student and are just curious, you can enjoy these videos too. Now, with that little intro out of the way, let's get into the first topic, logic gates. Computers are awfully complicated machinery, with this complexity stemming from minuscule sizes. However, any computer in the whole world follows a basic diagram called the von Neumann architecture, which can be boiled down to these basic four things. Every computer in the whole world follows this model. It takes an input, processes it, stores data if needed, and then gives back an output. An example of an input device could be a mouse, keyboard, or microphone. An example of an output device could be a monitor or a speaker. And finally, an example of storage could be RAM or a hard drive. Despite computers being highly complicated, in the end, it follows a simple diagram like this. Now, how is this process able to be done in computers? Through logic gates. In a nutshell, a logic gate is an elementary building block of a digital circuit, usually with two inputs and one output, which then decides whether or not it should let currents flow through. There are three main types of logic gates: AND, OR, and NOT. Let's start with AND. It will only let current through if both of its inputs are on, hence the name. It will not let current through if one of the inputs are on, or if neither are on. We can make a truth table for this. As you can see on your screen, the outputs will only be 1 if both of the inputs are on. Simple, right? The next gate is OR. It will only let current through if at least one of the inputs are on. Here is a truth table for this one. And the final main logic gate is NOT. NOT will only let current through if the input is 0. Basically, it does the opposite of the input. Here's a truth table for NOT. Now, here's a diagram of all three gates being used in a circuit. By looking at these inputs, can you figure out if the light bulb will be on or off? Pause the video and have a go. Yep, that's right. The light bulb will be on. The OR gate is triggered because it has one or more inputs. The NOT gate is triggered because it has the input as 0. And the AND gate is triggered because both of its inputs are 1, thus lighting up the light bulb. Isn't that cool? Knowing that every computer on this planet is made up of billions of these tiny simple circuits, yet they can land humanity on the moon, and that was only 50 years ago. The next three gates that I'm about to show you are lesser known, but are still widely used. That is, the NOR, NAND, and XOR gates. The NOR and NAND gates are pretty self-explanatory. Just like a NOT gate, they do the opposite of what the input is. For example, a NOR gate is basically a NOT gate but with two inputs, thus works the same. Here's the truth table. The AND gates, however, will only fire if neither inputs are on, or if one of them is. If both inputs are on, then it will not fire. Here is also the truth table. And the final gate of this video is a XOR gate, which is short for exclusive OR. This gate basically only lets current through if only one input is on. Unlike the OR gate, it will not accept both inputs to be on. You should be very familiar with this gate, since it is usually found in your house. If you have a staircase, you might have noticed that there are two switches for the lights. And if you turn on the light downstairs, and then walk up and hit the switch, the light then turns off. This is exactly the same concept. Here is its truth table. One thing that needs to remind you about is that the shape of these gates really do matter, since adding a circle can mean a difference between an AND or a NAND gate. Now that you know how they work, you might want to play around with them and try to create some kind of system of your own. Well, fear not, for there is Logically. In this website you can create your own logic circuits for free. I highly recommend it, and I will have it linked in the description. I hope that you learned something new and enjoyed this video. Next time I'm going to be covering binary and hexadecimal. So with all that, peace out.